Good morning. We continue with our lecture on precipitation from solid solution, and main purpose or objective of this topic is to illustrate or is to show you how by controlling processing we can get an optimum distribution of precipitate, which will give you stable and high strength or desired properties. Now, last class we looked at few of these. We learnt about terminal solid solution. We learned that any terminal solid solution, when it is quenched from the single phase region and it is in the supersaturated state, and if it is aged, there is a process of precipitation. We looked at the thermodynamics of the process of precipitation. We also talked about the energy barrier which has to be overcome so that precipitation process can take place or continue. So, that means we talked about a bit of kinetics of precipitation. We talked about the homogeneous and heterogeneous precipitation and how they can be controlled, and we learned that to get a good uniform distribution of precipitate in the matrix, you have to somehow promote homogeneous nucleation rather and suppress heterogeneous nucleation. We talked about different types of precipitate like coherent precipitate, where the surface energy is extremely low, but it may have some amount of coherency strain associated with it. On the other hand, normal precipitate we know about, they are incoherent, and all incoherent precipitate has high surface energy. That means, if in a matrix alpha, that alpha beta beta precipitates, there will be an alpha beta boundary, and this is of the order of quite high, maybe 300 or 400 millijoules per meter square. Whereas, coherent precipitate, this surface energy will be extremely low. It could be 10, 20 millijoule per meter square, and you can also have some intermediate precipitate in between, which are semi coherent precipitate. And today we will look at precipitation hardening, the mechanism of precipitation hardening, and we will talk about few commercial alloy, and we will know about spinodal decomposition. This is also a technique to get in certain alloy system, we can get a precipitation can take place by a process where you are likely to get uniform precipitate in the matrix. Now, last class we introduced the concept of that metastable precipitate. This is the beta, say suppose this is the solid solution, which is that supersaturated alpha. So, say suppose we have this is the free energy composition diagram for the phase alpha, which is the matrix, and this is the free energy composition diagram for the precipitate phase beta. And we know under equilibrium, you can say this is the composition alpha 1 will be in equilibrium with beta, but this has a high surface energy. So, therefore, kinetically I mean you need to provide some amount of activation, otherwise I mean this process is difficult. That process, it is not kinetically favorable. You have to give some amount of undercooling or some amount of supersaturation, only then precipitation can take place. Whereas, if you have a metastable precipitate, a coherent precipitate, say something which is shown here. So, thermodynamically it is little unstable. So, it has higher free energy, but look at what happens here. If this is here, you know, this has low gamma, gamma is low, this is incoherent that stable precipitate, gamma is high. Now, when this low gamma, it is preferred because it will have a low activation hill to overcome. So, this is more likely to form with a lower degree of supersaturation, but when it forms, look at what is the composition of alpha with which it will remain in equilibrium. You see, you draw a common tangent, that it means, say this is the composition of B in alpha, which can be in equilibrium with this particular metastable precipitate. So, what it means, say if we say that this free energy composition diagram corresponds to this phase diagram, this is liquid plus alpha, this is alpha, and we are considering, let us say at this is the temperature at which we have drawn this free energy composition diagram. So, now this is alpha 1, this is alpha 2. So, that means, so say this is the solvus line for the stable precipitate beta, this is the solvus line for metastable precipitate or coherent precipitate, it's a beta prime. So, similar thing, and many cases we may find not just one, this process of precipitation can take place through a number of metastable precipitates. So, in short, what we can say, metastable precipitate have higher volume free energy, they are that way they are unstable, but lower surface energy because of favorable crystal structure, and that means very little perfect coherency or very little lattice mismatch. Now, if you look at we did derive last class that expression for that activation hill, and which you will see here if you go back, that for in the case of precipitation process, if you consider recall your earlier lecture, we calculated this activation hill, and this activation hill is inversely proportional to the square of the sum, that is volume free energy plus the coherency, that strain energy. So, strain energy also plays an important role. Now, look at it, say suppose if you have a metastable precipitate, what is going to change? Metastable precipitate will have low surface energy. So, that means gamma alpha beta, this is low. So, that means if gamma alpha beta, there is a normal precipitate is of the order of 500 or 400 millijoule, gamma alpha beta prime may be of the order of 30, 40. So, if that is so, what you get immediately, you see that your activation, that critical nucleus size, this becomes smaller, this is small. So, this becomes smaller, and also that activation hill which it has to overcome, this also, this term will dominate. So, this also will be lower. So, what is shown over here, that means metastable phase, it has less activation, that height of that activation hill is lower. So, therefore, it is will be kinetically favorable, because if you recollect your earlier that rate of nucleation or process, or you can say this is proportional to the exponential, that activation hill delta G star over R T. So, the number of nuclei that forms, if this is low, then you can easily see from here that you will have more number of nuclei, or rate of nucleation will be high, and therefore, metastable precipitate, since it has lower surface energy, it has lower activation hill, its nucleation is kinetically more favorable than stable precipitate, and that is why this is the way precipitation takes place in any supersaturated solid solution. So, here we have written 1, but in many alloy system there may be multiple intermediate metastable phases. Now, aluminum copper system has been most extensively studied. In this particular alloy system, the process of precipitation has been extensively studied. So, let us, if we refer to this, it is shown here. Say this is the supersaturated solid solution, that free energy diagram, and here you have number of intermediate stages. Initial precipitate that forms, it is just some cluster of copper atom in certain aluminum, that lattice, say some places you have number of copper atom will form a cluster, and which is fully coherent, but it is unstable. No doubt free energy, volume free energy is much higher, but it is perfectly coherent. So, with this, if you can draw a common tangent to this phase, so this is the composition with which it will be in equilibrium. So, this is, let us say this is say alpha 4. Similarly, there is another, it does not go through just one stage, there are multiple number of, depending on the composition, you can have multiple number of precipitation in intermediate precipitate. The first precipitate, which is cluster of copper atom, this is known as Guiner-Preston zone or GP zones. Next precipitate is theta double prime, which is shown here. Its stability is shown by this free energy composition diagram. Next is theta prime. So, these are all coherent, and finally, this is the stable precipitate theta, which is the final precipitate, and this is actually is CuAl2. Now, when these precipitate form, these precipitate they are, this is just a cluster of copper atom, but when this whose crystal structure will be very similar, copper also collection of copper atom also will have a face centered cubic structure, aluminum has a face centered cubic structure. So, this also will, but it is a very thin, say maybe one monolayer kind of thing, and just a cluster of few copper atom in aluminum lattice. Next is theta 2, it has a definite crystal structure, we will come to know about it, and certain direction its lattice will be exactly parameter may be exactly similar to that of aluminum. So, that will be the preferred plane on which this precipitate will form. This also has a little different structure than theta double prime, and finally, so it goes on changing, and you can see this has the highest solute content. Next is alpha 3, this is alpha 4 is GP zone, this is alpha 3. So, this is this one, and this is you can say, I think it does this is alpha 4. So, what we can say, this is the Solver's curve for theta, that is that alpha 4. This represents the alpha 3 line will be somewhere like this, then alpha 2, then alpha 1. So, therefore, depending on the temperature and where you are aging, say if you are, this is the composition of the alloy and you are aging at this temperature, it will pass through all these intermediate steps. But if it is, say somewhere alloy content is here and you are aging it at this temperature, in this case only precipitate which is possible is theta prime and theta. So, that means the sequence of precipitation process will depend not only on the composition, but also at the temperature at which you give the aging treatment. Now, this if you look at this table which gives the lattice parameter of the different phases we talked about, and maybe you can look at the computer, that here it will be clear, which are listed. GP zones, the type of precipitate is coherent and its shape is that of a disc, and it is just a copper cluster. So, why it is? Because in one direction only the lattice parameter they will be matching, in other directions in the one plane only. So, if it tries to grow perpendicular to the plane, it loses coherency. So, therefore, it will be restricted, the shape will be most of the cases disc or thin plates. Theta double prime, it is coherent, this has a tetragonal structure, the lattice parameters are listed here, these are the values given in angstrom. Theta prime, this is partially coherent. Here this is also tetragonal, these are the lattice parameter, and incoherent precipitate is tetragonal, and these are the lattice parameter. And if you look at the lattice parameter of pure aluminum, which is 4.04 angstrom, you find from between this and this there is no chance of forming any coherent precipitate. I mean this will be totally incoherent, but if you look at this and let us say theta prime, there is a slight in this particular, that is that cube plane, that is 100 plane. It can form on 100 plane because lattice parameter they are perfectly matching, but if it tries to grow along the c direction, there will be lattice mismatch. So, which will cause to higher amount of strain. So, similarly here also similar thing is happening. Now, this is the diagram we just talked about. This is the solubility of metastable precipitate. This will depend you know, which are shown over here. This is the solubility solvers curve for the stable precipitate, the theta. This is the solvers curve for theta double prime. This is solvers curves for theta prime, and this is the GP zone. And suppose and let us say and let us say look at that, if you age this, how will that process of precipitation take place? Process of precipitation will be a time dependent process. So, rate of nucleation will depend on the magnitude of undercooling. So, what mean if you look at over here, you see that means if you are keeping, this is the alloy, let us say, as a particular composition, and we have kept it at temperature T4. T4 means here. So, here you can see this is on the lying on the solvers curve. So, even if you keep it for infinite length of time, there will not be any precipitate. So, this axis is the temperature, and here we are trying to plot the time it takes for the precipitation to start. So, in this particular case, here there is no supercooling, it takes it will continuously, it will remain in the state of alpha. But when you come down here, there is a degree of supercooling. Higher this degree of supercooling, higher is the driving force. So, therefore, nucleation becomes favorable, and the kinetics will be determined that movement of atom to form the precipitate, the atom you need to move the atom, you have to give the time, you have to give time for the atoms to move, let us say copper atom to move in aluminum lattice, and this is a process of diffusion, and diffusion we know, higher the temperature, higher is the rate of diffusion. So, therefore, as you go down, diffusivity decreases, diffusion becomes slower, and there is an optimum condition here. So, the two things they vary in the opposite way. that is rate of nucleation is faster, higher the supercooling, and rate of diffusion becomes slower if the temperature becomes lower. So, therefore, there will be an optimum case where you will have the maximum rate of precipitate formation. So, this is the case where the precipitate forms in the shortest possible time. So, here which is the precipitate? Here you have GP zone. So, you will have alpha plus GP zone. Similarly, this precipitate, second precipitate theta double prime will try to form when this solvus line is crossed. So, this is the solvus line. So, this also will have a C shaped nature, and this is theta prime and this is theta. So, that means if you want to give a proper solution hardening treatment, what you need to do, you have to heat it above the solvus, say somewhere here. First you quench. So, if you quench, you can get a fast rate of cooling, you must avoid this nose. So, rate of cooling will be faster than this point, particular point, and after that you will heat it, you will take it, heat it and age it at a particular temperature. If you do it here, you will get theta double prime. If you age it here, say suppose if you age it, so normal aging so, I think you need to make a correction. This is the GP zone actually. So, I think here you will have alpha plus GP zone. This is, so T1 is the temperature. If you age it below T1, you will have alpha plus GP zone. I am sorry about it. This is alpha plus theta prime. Next is alpha plus theta, this is theta here, because between, if you are aging here, the only precipitate which can form is theta. If you come down, then only theta double prime will form. So, therefore, if you are aging somewhere here, so what happens? First the GP zone will form, then it will cross this line, you will have theta prime forming, then this line, then this. So, last precipitate to form will be theta. So, the thing is, you remember, that means this sequence of precipitation will depend on composition of the alloy as well as the aging temperature. Now, when this process of precipitation takes place, you have different types of precipitate forming in the matrix, and obviously, when this precipitate form in the matrix, what it will do? It will make it will process of deformation more difficult, because we have learned that metals deform by movement of dislocation. So, this precipitate gives, say in the matrix, if you have in the matrix you have precipitate, so dislocation which is there, it will be difficult for it to move or cross this precipitate. We will see how it is, how this takes place later. So, that means when this precipitate form, you will have some additional strengthening, and this is shown by this, and this can be followed by measuring the hardness. And if you measure hardness, usually the hardness is measured in weakest pyramid number, and which is shown over here. So, if that alloy has a 2%, you possibly find that here that alloy composition is such. If you go back to the previous diagram, you will see that possibly you will have GP zone, and after that you will have this is theta prime. So, similarly, but if you have 4.5% copper, possibly you will see this is the where you will have GP zone, this is theta double prime, then theta prime, and subsequently when it overages this side it will become theta. And you will find that effect of composition has a significant effect on the extent of hardening. If you increase copper, actually you are increasing volume fraction of precipitate. So, if the volume fraction increasing, and secondly you can also control, if you have a more particles and if the particles are small, the distance between the particles also will be small. So, that will provide as a more effective barrier to dislocation movement. So, that means the extent of hardening will depend on the chemical composition, that alloy content, and as well as it will also depend on the time of aging. It will also depend on the temperature of aging. So, if you age at a higher temperature, you have less number of precipitates, say suppose if the highest temperature over here which is shown, then there is no chance of GP zone formation. GP zone formation takes place at a lower temperature. It solvers. So, this temperature is higher than GP zone solver. So, here you do not see GP zone, whereas here you have GP zone. So, here you will have theta double prime, then theta prime. And you will also see if you increase that higher temperature, higher the temperature, the peak also of hardness comes down, and it is attained at a quicker, it is attained at a shorter time. So, that means process of precipitation is faster. So, here it will be difficult to control the precipitation process. So, therefore, to get good amount of strength, the lower aging temperature will be preferable. Now, a point about that whenever a precipitate forms, actually it is whenever a precipitate forms, say here, even if it is coherent, there will be strain field associated with it around that. So, therefore, and this strain, that means there will be a strain energy apart from that volume free energy, and this will be proportional to the volume of the precipitate. And secondly, opposing factor is whenever this precipitate forms, a incoherent precipitate forms, this is incoherent precipitate, this has high gamma, this is high. So, in one case this is high, another case this is high. Now, we know that means this volume actually will be proportional to the dimension, basically the dimension. If we say the thickness, it is possible to show that volume will be proportional to this, whereas surface area will be proportional to the thickness square of the thickness. So, in fact, it is possible to show a simple calculation which is shown on that computer screen. If you look at that, how do you calculate the strain energy? Strain energy will depend on, will be proportional to the volume, the modulus, volume of the precipitate, modulus, and the lattice mismatch. Delta represents lattice mismatch, and therefore, and nu is the Poisson ratio, which is usually around 0.3. So, we can make some approximate calculation. That means, this volume will be equal to, if you assume it to be disk, say a disk, and if you assume that there is a shape factor A. So, this disk, you assume disk may not be perfectly circle. So, so there may be a shape factor. So, it is proportional to this area of the disk is proportional to this square of T, and then to get volume you have to multiply by the thickness, this thickness is T. So, you get this will be equal to T cube, whereas the area of the same disk, if you try, you can find out the area of the top surface and area of the cylindrical surface. If you can find out, then you get the surface energy, and if you equate the two. So, this gives the switch over, and you can find out by equating the two, there is a critical thickness where both this and this are equal. And what does this mean? So, look at over here, if you plot this energy and this is T. So, this varies as T cube, this varies as T square. So, T cube, because T dimension is quite small. So, initially here the preferred precipitate will be coherent, but when it grows crosses this critical point, in that case incoherent precipitate will be more preferred. So, that means there is a critical dimension as the precipitate tries to grow, it will, that lattice mismatch will increase, and finally, it will be replaced by incoherent precipitate. Now, let us look at the process of hardening. What we said that strength of a metal, it depends on its ability or to move a dislocation and the lattice. Now, suppose here this is a grain, this is a precipitate, and you have a dislocation. If it is somewhere here, it will be straight, and when you apply shear stress tau, the dislocation you push it, and now this opposes the dislocation movement. So, here when it comes near, it becomes bent, and after that one possibility is it can cross this and leave behind a loop. So, one mechanism of this dislocation movement in a particle and a precipitate containing alloy is the looping around a precipitate, loop and move. This is one. Another possible way will be, if this is the precipitate, you apply stress, and this stress here is sufficient to fracture the precipitate or shear the precipitate. In that case, this is how the precipitate has been sheared, and this moves here. So, what happens after shearing? Some additional area is being created, additional area where it will have some surface energy is being created. Secondly, if the precipitate had some ordered structure, that ordered is disturbed, and this. So, that means to fracture you need some additional, or to move to slip or shear the precipitate, you need a sufficient amount of stress for this to happen. So, this is the other mechanism. There is also a possible mechanism cross slip, but we will not consider here. I think these two we feel is most important to explain or understand the process of precipitation hardening. And now, same thing is shown a little detail here. If you have a distribution of precipitate in the matrix and you have a dislocation which is bent over here like this, when you apply, this will happen when you apply a shear stress tau. Now, you increase the stress, it will bend further, and it can move something like this around this, and look at, if you have assign a dislocation direction T. So, this is the direction of the dislocation, and it has a Berger vector. Say suppose you say this is the Berger vector B. So, there will be cases here, so in this case dislocation direction is like this, Berger vector is like this, whereas over here the dislocation direction is dislocation Berger vector is this, dislocation direction is this.
So, that means nature of the dislocation keep changing, you know, and it is quite likely to happen. Say one case it will be a positive dislocation, this may be a negative dislocation. So, ultimately they will try to join, and then when they join, what happens, a loop is left behind and this dislocation moves, and later on it becomes straight. And with this assumption, it is possible to work out the relation magnitude of the additional the CS stress which you need. And if you remember your earlier lecture, that additional CS stress which you apply, the radius of curvature, it depends on that is a function of that CS stress that you apply, and this is given by, this is the line tension T over Burgess vector B, and this is the radius of curvature. Now, the minimum radius of curvature, it is possible to calculate, and we had done it earlier, and if you substitute this, an expression for T is usually roughly proportional to 0.5 GB square times ln. This is we can take this is actually d over, this d is this precipitate spacing. So, what we can say that dislocation, the effective, the strain field of the dislocation is half of this. So, this is, so we say that this is the area that dislocation, the strain energy of the dislocation is located within this area. So, therefore, here you substitute d, and also it is possible to relate d with the volume fraction and radius of the particle, and this is a simple stereological derivation which I leave it as an exercise. It is possible to show that if you have uniform particle of radius r distributed in a unit volume and the volume fraction of precipitate is V, it is possible to show that the distance between the particle will be given by this. So, if you substitute over here, you get this expression. So, in short, what it shows that this additional, that strengthening which you are getting is proportional to the volume fraction root of volume fraction of precipitate over the size of the precipitate or radius of the precipitate, which is quite important, and we will use it later. In the same way, it is possible to do similar calculation for particle cutting. We will not go into the detail of the process of calculation, but here two things happens. When the precipitate is sheared, here if there is a this is an ordered precipitate. So, you have bond A B type bond here, here is A, here is B. So, if you slip it, you may find, say then if you slip it, you may find this is A, this also becomes A. So, that means that order gets disturbed, and this, that means this will have an additional energy, and this is called antiphase domain boundary, and there is some antiphase domain boundary energy associated with it, and this is antiphase domain boundary energy can even be quite large. It could be around 300 millijoules per meter square, whereas coherent precipitate we have seen maybe 1/10 of this. And secondly, whenever this process of shear takes place, now you have new surface created. This is the additional surface created. So, this will have another energy, that surface energy. So, this will need, for this to happen, you have to apply some amount of additional CS stress. And how can you, what is the nature of this relationship which is shown here? If you calculate it with a little rigorous calculation with the antiphase domain boundary, you get this also. Essentially what it shows that it remains f to the power a power 1/3 r to the power half. This is delta T, this is for antiphase domain boundary and this is for that new surface created. So, that means this increases as the particle grows, whereas looping, for looping delta tau loop, this is inversely proportional to R. So, this is quite important and we will look at that implication of this, which is shown here. So, this is a plot of the CS stress and this is the particle size. Now, this is the ideal strength of the crystal, this is the critical resolve CS stress. So, this is the limit that you can have. Now, here this line plots that looping stress, which is proportional to root f over r, it is inversely proportional to r. So, therefore, r decreases, this goes up, whereas when you have just aging has started, you do not have any precipitate. So, initially what happens, some amount of precipitate will form and this will follow this plot. So, this is the precipitation stage or the aging process. So, this volume fraction as well as R keeps on increasing. So, this is for a particular alloy composition, say maybe this is for, let us say 2% copper. If you increase more copper, where you will have more volume fraction, in that case this may follow a plot like this. So, what it shows, actual process of precipitation is, as the precipitate forms and grows and the lattice, say suppose this is a grain, two things happening, you have a precipitate forming and this precipitate also will grow. You have another precipitate forming and this also keep growing. So, with time two things increases, F increases as well as the precipitate, this also increases, and this defines the limit, that is the maximum strength that you can have in the alloy system. So, this in a way you can say that this defines that maximum strength that you can get in a precipitation hardenable alloy. So, this you can do primarily by controlling, I mean you want to increase it further, you have to increase the solute, and thereafter when the maximum, but there is a limit to what F can attain. So, there is an equilibrium limit, and when this limiting value has reached, you can say that you have reached over here, and after that what can happen? When that limiting size, that equilibrium amount of precipitate has formed and you are still aging, you have thermal activation, there the precipitate can grow, and when it grows again, that is a precipitate course and strength tries to drop, that is following this path. So, this is the mechanism of strengthening, and this is overaging, which is shown over here. Actually, this overaging takes place when this precipitate grows, because if you have a one precipitate, another large precipitate. So, they will have different thermodynamic stability. The smaller precipitates are thermodynamically unstable, they have higher free energy. These are coarse precipitate, which is thermodynamically more stable, they have lower free energy. Now, if you draw that, you can see this precipitate here, that concentration, say if this is alpha 1 say composition, this is alpha 2. Now, here smaller precipitate, here you have concentration is alpha 2, here concentration in alpha 1, and alpha 2 is greater than alpha 1. So, there is a concentration gradient. So, this will diffuse, and finally, this will disappear, this will grow. So, this is the process called Oswald ripening, and it is possible to show that the process of ripening follows a kinetics, say something like this. This is the radius of the precipitate, this is say original initial precipitate size. So, that means the R cube is actually proportional to a constant times t, and k, this is the rate constant, this is proportional to. So, definitely the diffusivity will play one important role. Second is the surface energy, when they are growing, in that case net surface energy decreases. So, surface energy is also a driving force, and another important driving force is the amount of solute you have or solubility that you have, that equilibrium solubility limit. Then you have larger, you can then if this is large, that is there can be a large difference, that concentration gradient can be there. Now, you think in order to design precipitation hardenable alloy and to improve its strength, say particularly precipitation hardenable alloy, they have lot of application, they are applied even at a high temperature alloys, and there if you want to improve that high temperature strength, it will be subjected to high temperature exposure. So, therefore, at high temperature when it is in service, you have to reduce K. How can you reduce K? There are three ways. You can play with, bring down the diffusivity, bring down gamma, bring down the solubility limit. So, this is the, and if you look at some of the common high temperature alloy, the mnemonic you have a gamma, gamma prime is the matrix, gamma prime precipitates, and this gamma, gamma prime precipitate, they are perfectly coherent. So, they have very low surface energy. So, that is why they are high temperature stability is very high. So, this is a very popular high temperature alloy. Another example for a low Xe, so oxides solubility is very low in matrix. So, if you have this thoria dispersed nickel, so in nickel matrix if you have thorium oxide dispersed, then you can say that solubility of thorium the oxide in nickel will be very low. So, therefore, this thoria particle will be a perfect, I mean they will be stable precipitate, stable dispersed solid, which will restrict the movement of dislocation. Same thing can happen thoria dispersed tungsten. Another is low alloy steel is very often used for high temperature application, boiler tubes or steam turbine blades, and here see if it is a plain carbon steel, the carbon diffusivity is very high. So, therefore, the carbide will coarsen. Now, you can bring down the coarsening rate of carbide by adding some alloy element which goes into carbide. So, strong carbide formers if you add, you can decrease that coarsening rate of precipitate and increase the high temperature stability of low alloy steel. Now, a quick look with another method of precipitation, which is called spinodal decomposition. It does not take place in all alloys, it typically takes place in alloys where you have miscibility gap, say something like this, say a miscibility gap like this. Say if you have alpha and here is a region, it breaks down into two solid solution below a particular temperature. So, in this case if you look at these free energy composition diagram, this is X B atomic, this is A, this is B, this has this type of a plot. Now, here if you look at an alloy over here and suppose, and let us say that whether a small fluctuation, then in any alloy the atoms are not stationary, the atoms keep moving, that solute atom will keep moving. So, at any instant the concentration at a particular point can change. Now, let us examine whether this small change in composition will be stable or unstable over here. So, here if you look at over here, in that case, say suppose this is a small change in composition, then the mixture will have this free energy, whereas the solution has the solid solution has this free energy. So, this is solid solution has lower free energy, more stable. So, here this type of fluctuation will die, it cannot grow. Whereas, if you look at somewhere here, if there is a small fluctuation, so this is alpha 1, this is alpha 2, and the free energy of the mixture is this, free energy of the solid solution is this. So, that means here this fluctuation will be stable and it will grow. So, something like this, say this fluctuation is there, this is trying to grow like this, it has grown and finally, it has formed this precipitate. So, this is say suppose we say that this is alpha 2, this is alpha 1, this composition, this is alpha 2, this area. So, that way. So, this corresponds to one composition, this corresponds to alpha. So, this corresponds to alpha 2, this lower one corresponds to alpha 1. So, what is the advantage of this precipitate? If such small fluctuations you can let it form into a precipitate, it will be a homogeneous precipitation, you will have uniform precipitate all through the matrix. And you can easily show that the condition under which this take place, if you look at the slope of this curve, the slope here is increasing, somewhere in between it becomes maximum, again the slope comes down. So, if you try to do it, you will find that somewhere the slope of this, if you define this as G slope, somewhere the slope is let us say here is 0 and then somewhere slope will become maximum and come down. If you differentiate it again, you will find you will again get this is 0. So, again you will get this slope is increasing and then decreasing. So, it has a high slope, but later on it decreases somewhere here. So, there is a composition where you can say there is an inflection point, say if this is the type of a free energy composition diagram, say this is the case, here you can say the double differential d2g, this will be 0. This is where the inflection point and this point is called spinodal. So, what you have, if you have an alloy system, this is a spinodal, this is the solver's curve and here you have this two type of precipitation. It is possible to show this is the spinodal point at a particular temperature. So, within this you can have small fluctuation stable. So, within this you can have homogeneous precipitation, uniform distribution of precipitation. Here it will be a normal nucleation and growth. And this is the case we are considering where the precipitate is incoherent. If the precipitate is coherent, we can extend this solver's curve for coherent precipitate will be somewhere here. Similarly, for coherent precipitate you will have a different spinodal. So, main advantage of this is a spinodal decomposition is possible in many alloys, which is listed here. And next, if you look at this slide, it gives a few common age hardenable alloys which are listed, and each of these, this we talked about in detail, but similar sequence of precipitation is followed in everywhere. It goes through zone, some coherent precipitate, finally incoherent precipitate, and these are listed here. Some of the aluminum base alloy, some common copper base alloy and a nickel base alloy. And it is possible, I mean this list by no means is comprehensive, there are many other alloy systems. So, to sum up what we looked at, that what we understood as all terminal supersaturated solid solution where coherent precipitates form can be given, can be age hardened, and the fine precipitates, you need very fine precipitate to get precipitation hardening, and this magnitude of that spacing is of the order of 1 micron, and to get a good precipitation hardening, you have to suppress heterogeneous precipitation, which is possible when gamma is low and there is some amount of coherency strain, and the strength is a function of particle size and volume fraction. We looked at effect of composition, aging temperature and time on the process of hardening. We looked at the mechanism of hardening, that is looping, dislocation looping and particle cutting. We also looked at over aging, which leads to loss of strength due to particle coarsening. Thank you, and next class we will take up another topic. Thank you.